Welcome to ElectronLine. Here's another example of how to find the currents and the voltages in an inductor circuit. It's a fairly simple circuit, but yet there's a lot of work to be done. We're given two inductors in parallel. That parallel branch is in series with this third inductor. We're given that the current as a function of time to the second inductor here is equal to 0.6 times e to the minus 2t amps, and that the initial condition of the total current when time equals 0 is equal to 1.4 amps. We're trying to find all these various things. Starting with the initial current when time equals 0 through inductor 1. Well, to do that, since we know that the total initial current through the entire circuit is 1.4 amps, we need to find the initial current through inductor 2, subtract that from the total to get the initial current through inductor 1. So let's do that first. Let's find the initial current, I sub 2 through inductor 2 when time is equal to 0. So we plug in 0 for t in this equation. This becomes equal to 0.6 e to the minus 2 times 0. That's of course in amps, which is equal to 0.6 times 1 amp, which is 0.6 amps. That's the initial current through inductor 2, right there. So now that we want to find the initial current through inductor 1, all we have to do is subtract that amount from the total. We can see that I sub 1 when t equals 0 is equal to I total when t equals 0 minus I through the second inductor in that branch when time equals 0, which is equal to, that's a 0 by the way, which is equal to 1.4 amps minus 0.6 amps, which is equal to 0.8 amps. I think what we need to do, instead of trying to find the current, I think it would be easier to find the voltages first. Let's find the voltage across inductor 1. That, of course, would be the same as the voltage across inductor 2. And then we can, from that, figure out the voltage across inductor 3 and the total voltage. So let's try that. Voltage across inductor 1. Well, I know I can do this. Voltage across inductor 2, which is a function of time, of course, is equal to the inductance, L sub 2, times the rate of change of the current through that inductor. So why am I doing this for inductor 2 when I'm trying to find it for inductor 1? Well, because I know that the voltages are the same, and I'm given the current through inductor 2, so it's easier to use that equation. So this would be equal to L sub 2, which is, here we go, 6 henries, multiplied times the rate of change of the current through 2, which is this equation right here, which is 0.6 e to the minus 2t. And that, of course, would be in volts. Taking the derivative of that, we get 6 times, the derivative of that would be 0.6 e to the minus 2t multiplied, and I want to close the bracket here, multiplied times the derivative of the exponent, which is a minus 2, which is equal to 6 times this, that would be 3.6 times 2, that's 7.2 with a minus 7.2 e to the minus 2t volts. That would be the voltage, I forgot my minus sign. Here we go. That would be the voltage across the second inductor. And of course, we know that V1 is equal to V2, so we can write V2, which is equal to V1 as a function of time, is equal to this. Strategy is as follows. We now know voltage across both of these inductors. We know the current through the second inductor, but we don't know yet the current through the first inductor. And of course, the two currents combined will be the current through this inductor. And now once we know the current through this inductor, we can find the voltage across that inductor. So the next thing we need to do is find the current through inductor 1. For that, we need to use the following equation. We can say that the current I through inductor 1 as a function of time is equal to 1 over the inductance times the integral of the voltage times dt. And of course, we'll have to add to that the initial current, right? We will have to add to that the initial current I1 when time is equal to 0. So that will be the current plus the initial current. All right. So let's go ahead and plug in the numbers. This is equal to 1 over L1, which is 3 henries, times the integral of voltage through 1, which is this one right here, minus 7.2 e to the minus 2t. And we're going to evaluate that from 0 to t. And then we're going to add to that plus the initial current through I1. And where did that go? I1, T initial is 0.8 amps. So plus 0.8 amps. Can't forget about that. Now to integrate that, and of course I also need a dt in here. Can't forget the dt. Now to integrate that, I'm going to need a minus 2 dt. So I'm going to pull out a minus 2 here and put the 3.6 over here. So this is equal to 3.6 divided by 3 times the integral from 0 to t of e to the minus 2t times the minus 2 dt. So now I have my differential. I can integrate it. And of course, I still have to add to that the 0.8 amps of the initial current. So integrating this, it looks as follows. 3.6 divided by 3 is equal to 1.2 multiplied times, that would be e to the minus 2t evaluated from 0 to t, and I'll have to add to that the 0.8 amps. Plug in the upper limit, let's see what I get. So this is equal to 1.2 multiplied times, plug in the upper limit, I get e to the minus 2t, minus when I plug in the lower limit, e to the 0, that's equal to 1, plus 0.8 amps. So writing the result, we get I sub 1 as a function of time is equal to, we have 1.2 times the negative 1, that's negative 1.2 plus 0.8, that gives me a negative 0.4 plus 1.2 e to the minus 2t, and that's of course in amps. So now we have the current through inductor 1, we have the current through inductor 2. When we add those two together, that gives us the total current, which is also the current through inductor 3. So we can say that I total as a function of time, which is equal to the current through inductor 3 as a function of time, which is equal to, when I add those two together, that is I1 as a function of time plus I2 as a function of time, which is equal to, so adding this, which is minus 0.4 plus 1.2 e to the minus 2t amps, adding that to I2, which is 0.6 e to the minus 2t amps. And combining that, I get the following. This is equal to minus 0.4 plus 1.8 e to the minus 2t, and that's in amps. So that would be the total current in the circuit, which is also the current through inductor 3. That allows me to find the voltage across inductor 3, because we can say that the voltage V3 as a function of time is equal to L3 times the rate of change of the current I3 with respect to time, which of course I have over here now. L3 is 8 henries, so this is equal to 8 henries multiplied times the rate of change of this. The derivative of 0.4 is of course 0, and the derivative of this would be minus 3.6 e to the minus 2t. Minus 3.6 e to the minus 2t, which is equal to, that's 24, that's 28, 28.6 or minus 28.6. Let's see here, that would be e to the minus 2t, and that would be in volts. Let's make sure that was correct. 8 times 6, that would be 4.8. Add the 24, yes. So that would be the voltage across right here. So do we have everything now? Let's check it out. We have V1 and V2, which are equal. We have V3. We have I1, I2, I total. And it looks like we have everything we want to know about the problem. And that's how we do that.